Hi friends, in the last video we've seen by Bohr's third postulate that when an electron makes a transition from higher orbit to lower orbit, it emits a photon and the energy difference of those orbits will be equal to the energy of the emitted photon, right? So let this be the equation. I'll explain you. We know that the energy of photon is given by h times the frequency of photon, right? Minus m e power 4 by 8 epsilon naught square h square, and here you have n square. This is the energy of nth orbit, right? So let us put this one in this equation. So I'll get the energy or the h into frequency when the electron makes transition from I to F. That will be equal to, what is E and I? It will be minus m e power 4, and all these are common, h square, and here I should put n I square, and minus of minus plus, again I'll have m e power 4 by 8 epsilon naught square h square, and here I have an f final. The same equation can be written as frequency when the electron makes transition from I to F will be m e power 4 by 8 epsilon naught square h cube, and here you have nf square minus ni square. This is the equation, and you know that frequency can be written as c by lambda, that is speed of light by wavelength of light. So the same equation can be written in another form as c by lambda is equal to the same thing, or 1 by lambda is equal to m e power 4 by 8 epsilon naught square h cube c, and here you have the same thing. Is it resembling anything? Don't you think this is something similar to the formula which we had in Balmer series? Actually, all the series of hydrogen spectrum are given by those formulas which are similar to this one. We discussed this before. If NF is equal to 1, that refers to Lyman series, and if NF is equal to 2, you get the formula which is given by Balmer series, and if NF is equal to 3, 4, 5, you respectively get Bastian, Brackett and Punt series, right? So what is common in all of this? This part is common, and we wrote it as Rydberg's constant, you remember? So this should be my Rydberg's constant, right? M e power 4 by 8 epsilon naught square h cube by c. Of course, this is the Rydberg constant given by Bohr's model of atom. And note that all these are constants, m, e, epsilon, all these are constants, right? So if I put the values, I'll get to be 1.03 into 10 power 7 per meter. But the value I got in the value we got in the Balmer series was 1.09 into 10 power 7, right? But this value is something close to this, not too far away. So actual value accepted is this one, note that. So since this value given by Bohr's model is close to this one, that can what, certify or provide confirmation to the Bohr's model of atom. Hence we can treat that Bohr's model of atom is true. Of course there are some limitations, we'll discuss them at the end of this video. And hence when the electron makes transition from any of the higher orbits to n is equal to 2, observe this, then you have Balmer series, and since the arrows are pointing towards the nucleus, that is emission spectrum, that is energy is released, photon is released. And if the same thing happens in the reverse way, that is from n is equal to 2 to any of the higher orbits, then you get absorption spectrum, same Balmer series. And similarly you have Lyman, Bastian and Brackett series. You can actually write one generalized formula for all of the series, that is 1 by lambda is equal to R into 1 by nf square, that is final n, minus 1 by ni square. Just putting the value of nf as 1, 2, 3, 4, 5 respectively will give you the formulas for Lyman, Balmer, Bastian, Brackett and Punt series. And in each of these cases, I'd rather be specific, Ni should be greater than NF. that is 1, 2, 3, 4, 5 respectively here. Hope this is clear till now. Look at this problem. I have to find the wavelength of second longest wavelength in Lyman series, right? What is Lyman series? When the electron transition takes place from any of the higher orbits to n is equal to 1. That gives me Lyman series, right? So my NF can be 2, no, my NF is 1 here, and NI can be 2 or 3 or 4 and so on. And all of these will give me Lyman series. And note that when the difference between the energy levels of orbits is more, then I'm going to get the what? Smaller wavelength. More the energy, small will be the wavelength, right? So I want the longest wavelength. So I need to take that combination which gives me the smallest energy difference. So that will be n is equal to 2 will have actually the smallest energy difference, but I want the second longest wavelength. So second smallest energy difference will be between n is equal to 1 and n is equal to 3. Hope this is clear. And so I'll put these things in my formula. 1 by lambda is equal to r, and here I have to put nf as 1 Lyman series, and my condition gave me that ni is equal to 3, right? So 3 square, and this will give me my lambda as 102.51 nanometers, and this is in ultraviolet region. Note that this wavelength belongs to the ultraviolet region of electromagnetic spectrum. Yes, because Lyman series gives only ultraviolet rays or radiation, and Balmer series, as you know, gives visible light, that is 400 to 750 or something like that. Bastion and bracket both give you infrared region of electromagnetic spectrum. Hope this is clear. And the second part is also similar. Just the thing is that you have Bastion series, so your NF is going to be 3. So 3 square here, and third longest wavelength, right? So my Ni, what are the possibilities here? My Ni can be 4 or 5 or 6 greater than NF, or 7. So my third longest, this will give me the first longest, second longest, so third longest will be with 6. I'll put 6 square here, and this gives me the lambda as 1093.52. And note that this wavelength is far more than visible light region, that is, this belongs to infrared region, as we have discussed just now. The second postulate of Bohr's atomic model says that the angular momentum of electron revolving in that stationary orbits is multiple of h by 2 pi, right? Integral multiple of h by 2 pi. But it doesn't say why. Well, this man, de Broglie, gave an explanation for that. Here also, de Broglie said that electron should be treated as a wave. He also said that in analogy to waves traveling on a string, particle waves can also lead to standing waves under resonant conditions. You know what is resonance? Take a string, then when you pluck it, many number of wavelengths are actually excited. However, only those wavelengths survive or sustain which have nodes at the ends. I mean, which form a standing wave. I mean, the distance traveled by a wave down the string and back. That should be either one wavelength or two wavelengths or any multiple of wavelength. Start from here, go down the string and come back again. That is 2L. Should be equal to any multiple of wavelength. So your L can be n lambda by 2. So it can be lambda by 2 also. That is the case you are seeing here. And it can be something else also, like it is just the condition is that nodes should be at the ends. If any other waves are excited, then what happens? They interfere with themselves and they quickly drop to zero. That is why only those waves which give or which are in resonance condition, only they sustain. This is the explanation de Broglie gave. That is, when the electron is in resonance condition, then it doesn't radiate any energy. That is, it doesn't give electromagnetic radiation even though it is accelerating. So this shouldn't be the case because here it is not in resonance, and here it is in resonance, here it is in resonance. And how to calculate whether it is in resonance? Here we've started with one point and went down and come back again. for that total distance, it should be equal to a multiple of wavelength, right? So here also, we'll start with a point, and when we travel a distance and come back to that point, the distance we have traveled should be equal to a integral multiple of wavelength, right? What will be the distance traveled? That is the perimeter, right? It is 2 pi r, and that should be equal to an integral multiple of wavelength. So let it be n lambda, say. But what is the wavelength here? For anything which has a momentum p, de Broglie's wavelength is given by h by p. I think we have discussed this in previous chapter, I guess. So from this, what can I write? I can write that 2 pi r is nothing but n, and lambda can be replaced with h by momentum, right? And this is fine. What is momentum? Momentum is mv, for a particle which is moving with velocity v and having a mass m. So 2 pi r is nothing but nh by, I'll write the momentum as mv. And when I send these terms here, m and v, to the left side, I'll get mvr is equal to nh by 2 pi. Interesting, right? Mvr is nothing but angular momentum, and that is nothing but an integral multiple of h by 2 pi. That is what we prove. And hence, you can say that quantized electron orbits and energy states are due to the wave nature of electron. So this is the explanation given by de Broglie for the second postulate of Bohr's atomic model. Well, Bohr's atomic model has been able to explain the hydrogen spectrum, but the limitation is that this model is applicable to only hydrogenic atoms. Hydrogenic atoms means hydrogen-like atoms, which look or which resemble hydrogen. Like there is a nucleus and one electron. That's it. This should be the structure, nothing else. If there is another complex structure like, say, helium or some more electrons, the problem is you have to take the inter-electronic repulsion also into the consideration, and Bohr's model says nothing about that. So we can't apply this model to any of the higher elements. That's it for now. Keep watching. Bye.